Welcome to this video on the Memory Characterization project sponsored by GE Aviation and completed by Grand Valley State University engineering students. Our faculty advisor was Professor Scott Zeidema and our sponsor contact was Paul Baker. Now please meet the team. I'm Abigail Hendrick, the team captain, and I'm working with Charlie Dorn, Nick Behrens, Nick Bernhardt, and Zach Hales. I will be presenting the background on this project. So here's the situation. At high altitudes, high energy particles affect memory components. There's several ways they do this. They cause a latch up where a bit stays high when it's supposed to go high and low. They cause bit upsets where they switch a bit from 0 to 1 or 1 to 0. And finally, they can do that multiple times. These are called single event effects. Our challenge was to design a circuit card assembly to hold memory components that can be placed in a high-energy beam and monitored for single-event effects. We had to create both the circuit card assembly, or CCA, as well as software. The scope of our project includes this testing environment. As you can see, there is a beam path which passes through several DUTs that are placed on a table. Those little blue rectangles you see on the ADJ table are our circuit card assemblies. You can also see that there is a fixed table where power supplies and other peripherals will be attached. And finally, there's a 7-foot concrete wall, behind which is our software running on a Linux distro. This 7-foot concrete wall is for the protection of the user who is interfacing with the software. We had a couple key specifications. We had to use the same processor for all the CCAs. We had to have an adjustable heater. We also had to have adjustable point of load converters. And finally, we had to have a periodic output on our software. We created a design and presented it to the sponsor, and they approved it. However, there was a huge problem with supplying our chips for that design. So came the pivot. There is a global shortage on computer chips. In fact, it's at a crisis point where car manufacturers have to pause production. This resulted in us coming up with a daughter card solution. Now I will pass it off to Nick Bernhardt to discuss the performance of this solution compared to our specifications.
Thank you, Abby. So, as she mentioned, we had a few key specifications that we had to meet for this project, and I will discuss how we met each of those. So, our 4 key specifications that she outlined were that we would have to have the same processor for all of our CCAs. We would have to have an adjustable heater for our DUTs. We would have to have adjustable point of load converters for our DUTs. And we required a periodic output of the status and temperature, etc., of our entire system. So in order to meet the same processor for all CCAs, this actually proved quite challenging as we needed to provide both an interface to program memory as well as an interface to DDR memory. And this limited our processor choice by quite a bit. And so we ended up settling on processor choice of the Zinc UltraScale so that we would have an FPGA and a processor side so that we would be able to communicate with the processor side memory via the processor, and it would run the program from that. And then the FPGA side would be used to communicate with our DUT memory that would be tested for the memory interfaces that would need that extra DDR interface. So for the adjustable heater, that is a requirement that we were able to meet by supplying PWM to it from the processor. And then for the adjustable point of load converter, that was an integrated circuit that we found and then were able to place on the board and communicate with to provide multiple channels of outputs of various amounts that we could program digitally from the processor side. And then for the periodic output, we were able to establish TCP communication and send packets from the embedded side to the user side and display that information, that data that we gathered on the embedded side to the user. And finally, to discuss the user interface. So our goal with the user interface was to develop a command-driven user interface to be able to allow the user to enter a DUT, a test mode, and a test pattern all at once, and then be able to stop that test early if they need to. So here is our very simple command line driven user interface to allow the user to input those parameters, and then if they so desire, they can stop that test early once they run it. And with that, I'm going to pass it off to Charlie to discuss the key board parts and circuits found on in our design. Thank you.
Hi, my name is Charlie Dorn. Today I'm going to be talking about the software as well as some of the important hardware components of the MEMSAP project for GE Aviation. So as you can see, here's our software breakdown diagram. We have three different significant parts of software. So the first is the ARM processor. This is the microcontroller that most people are familiar with. The ARM processor handles the booting from the SD card and handles the general flow of the testing program. So it gathers data from the user side via TCP, sets up testing parameters, sets up the hardware for testing a specific DUT, and kicks off tests and stops tests. The user side program gathers input from the user via a command line interface and sends the testing parameters that the user has entered via TCP to the ARM program. The FPGA is part of the Zynq UltraScale. So the Zynq UltraScale is a hybrid ARM processor and FPGA. We're using the FPGA as a memory interface. So the FPGA provides us an extra DDR4 interface as well as a NAND interface. We use the Xilinx XCZU2CG with 2 gigabytes of DDR4 memory included on this card. Originally, we planned on using a just processor rather than the MP-SOC card. However, due to supply issues, we ended up using the card because that was available. This card has the processor along with DDR memory, as well as all the other peripherals that are needed to bring the processor up. This will connect to our board via these 4 160-pin connectors, as can be seen here. And this will actually be more cost-effective than our original solution, as it will allow one processor to be shared between multiple boards. Next, we'll talk about the Wiz850IO. This is our Ethernet module. We can communicate with the module via SPI from our processor, and it can communicate with external Ethernet devices via TCP or UDP. For our program, we're going to be using TCP due to its connection-oriented communication, as well as its robustness. The Wiz850IO uses a W5500 chip, which is a hardwired TCP IP stack internally, which means that we don't have to write all of the TCP IP stack ourselves in software, which saves us a lot of time. This device also has interrupt capability, which can notify us when a message has been received, so that we don't have to poll for messages, but rather we can just get an interrupt notification that we need to check for messages. This device runs on 3.3 volt input, and logic for the SPI is 3.3 volts. Finally, the point of load converter for our DUTs. This is a programmable point of load converter, which means that we can set the voltage as well as setting other important characteristics and reading characteristics from the device. So this device is on the I2C bus, and specifically it's a PM bus device. The PM bus is just I2C with predefined special commands that can be used to do certain things. For example, setting the voltage output, or reading the temperature, or reading the current draw from the device. The LTC3882-1 has internal NVM, which can be used to store desired configuration. For example, if we know that we want to power up with a specific voltage every time, we can store that in NVM so that every time the device powers up, it starts off at that voltage. This chip will allow us to output 0 volts to 5 volts, and has two separate output channels, which can be used for some devices that might require two different voltages. For example, some of our devices require a core voltage input as well as an I/O voltage input. And sometimes those are different values. So with the two separate output channels, we'll be able to power both of those with just one single chip. Next, I'll be passing it off to Nick Behrens to discuss the DUTs and the testing procedure. Thank you.
Thank you for the introduction, Charlie. My name is Nicholas Behrens, and today I will be discussing our DUT interfaces, as well as the memory testing for the DUTs. There are three memory devices that were integral for this project, those being the SPI NOR flash, the NAND flash, and the DDR4 memory part. Beginning with the NOR flash, it'll be communicated with over SPI communication via high-speed COM ports set up in EMIO configuration. Next, moving on to the NAND flash, that'll be parallel communication via high-speed GPIO pins. And finally, the DDR will be communicated with through the MIG interface on the Zinc UltraScale Plus FPGA chip. The Zinc UltraScale Plus was one of the few to contain all the necessary interfaces and a wide breadth of technical information and examples. Technical info was key for this, but most other chips didn't have the same interfacing capabilities as well. All communication will pass through the Samtec high-speed board-to-board socket. While seemingly not a viable option earlier on, sourcing and design constraints lended to the daughter card route, becoming more of a challenge that could be undertaken. With the Samtec parts, high-speed and promising signal integrity claims increase the viability of the daughter card option, hence why it was chosen for this design. The memory testing for each of the parts followed a similar testing pattern as is described in MEMTest 86. While MEMTest 86 itself wasn't used, parts of it and examples of it were used in the memory testing for the DUTs. Now the difference in the DUTs is that for the SPI NOR flash and the NAND flash, they'd be written to by paging, whereas the DDR RAM would be written to every 32 bits, meaning that a write sequence would occur in which the processor would write 32 bits to the DDR and then move on to the next address and write 32 more bits, and so on and so forth. Because MEMTest 86 needed to be purchased, MEMTest 86 was not considered as a part of the design. However, the individual tests from MEMTest 86 were considered because of the robustness of MEMTest 86. The algorithms included in memory testing include walking ones, own address, inverse address, moving inversion algorithms, random pattern, modulo 20, and a bit fate test. These are important as it was vital to get memory testing that wasn't simply sequential. The goal was to get testing that would be able to simulate somewhat of a real life scenario where you wouldn't just be accessing data sequentially, you'd also be accessing it in different areas as well. That essentially wraps up our design for GE Aviation in memory characterization. Thank you very much for listening, and have a good day.